Hey there, welcome back to COG 376. So, we've talked before about some of the background and theory of how you can conceive of n-gram models of language, right? Um, Today I want to get more into what n-grams kind of are, where they live in language, what their role is, and we're going to dig even deeper into how one might construct such a model and some of the ins and outs of using it. So, to start, I want to set the stage with this semi-classic YouTube video. Hang on a second.
Have you ever had a dreams that you had you could you do you want you could do so you do you want him to do you so much you could do anything?
Cute kid, right? He is kind of stuck in a bit of a loop, isn't he? Now, also, I don't think this video didn't get popular because it was about, making fun of the kid. It's just, this happens to everybody, right? It's you get a little bit stuck, you grasp for straws, you're not sure where to go, you're trying your darndest to get the words out, kind of like I'm doing right now. And you may end up using information that's not relevant to what you're trying to communicate. So he's not spouting just gibberish, right? He's trying to find his way to the concept he's trying to get to, which is essentially, did you ever have a dream that you could do anything, right? But the way that he is swinging from word to word, the words actually kind of make sense together. He has some filler words in there like and things like that, but did you ever, do you like, do you. But overall, he's not going anywhere with it because he's just kind of allowing his brain to kind of spit out the next word, right? The way we can think of this is that this kid is relying on the statistical regularities of language for something to say while he sort of spins his tires, right? He's trying to figure out where to go with this sentence. That essentially, I think, encapsulates the idea of why bigrams are useful, or n-grams. So, language learning in general can actually sometimes rely on these statistical patterns, right? We pair our understanding of words together based on how we hear them used together. Now, there's a whole lot of other stuff. You look at the linguistics. We already looked at the sort of the diagramming of sentences, the parts of speech matchers, right? You can make some pretty complex representations, and we often do. But not all of our language learning is just based on that. Some of it is about usage and usage statistics. So knowing that two words go together is a really useful place to start when you're trying to understand how they're used and what they actually mean. So in this way, you start out with this sort of very broad take on the meaning of certain words, and which you then may learn better of later. You may think the times you've said, "I'm not sure what that word means, but I know what it means in context." You are relying on the words around the word in question to pick up some of its meaning. Now, that doesn't always work if you don't know the noun in a sentence and there's no other context clues, and it might not help you. But that's more of the exception than the rule. Things that go together often have something to do with each other. So it also accounts for idiomatic language use to an extent. For example, how are you doing? Right? This is the common American greeting where you actually aren't asking how someone is doing, right? Their emotional state and their internal life and all that. You just know that the answer is good, how are you, right? It's almost devoid of content. It's just pattern matching. It's just the statistical regularity of, hey, I hear this all the time. So that kind of digs at how bigrams kind of fit into language in a general sense. We can also take a look at, how do you analyze bigrams? So here's that text from the kid. Have you ever had a dream that you had that, etc. If you look at the statistics of the bigrams of this, I guess this is a single sentence. The statistics of these bigrams, according to Google, in 2019, part of the Google Books project to capture as many bigrams as possible from all books that Google has cataloged. These are actually pretty high probability words, or at least pairings of words, right? So, for example, 0.01% of all bigrams. Now, 0.01% doesn't sound like much, but you think about all pairs of words, 0.01%, 1 in 10,000 pairs of words is that you. Wait, that's right? 10,000, 100%, 1, yeah. So that you, it's that common. So take any two random words that are right next to each other in all of language. Odds are 1 in 10,000 you're going to get this exact pair. Most others are far lower than that. Far, far, far lower than that. So this is the way we can examine how sort of common is the speech that is happening here. It's really kind of fun. You can dig into this yourself using Google's Ngram viewer. So you can explore Ngrams on your own. And the idea is that you can examine the statistical likelihood of Ngrams throughout the history of books cataloged and scanned by Google. Really, again, because the percentages are so low, this is more about looking at the natural occurrences of two or more, right? So in this case, we see that Einstein. You can see kind of the advent, right? So Frankenstein first came out in early 1800s. Somewhere in the midst of the 1880s, we get Sherlock Holmes, and its usage becomes more common. Einstein, he's born prior to the 20s. But he's not as popular in the end. Everybody knows him, of course, but he's not as popular. What am I doing here? What I'm doing is tracing the trajectory of the usage of paired bits of language to see how they move through history. Looking more, an interesting example here of Frankenstein's monster, Dr. Frankenstein, and Professor Frankenstein. Professor Frankenstein is nothing. That's not actually his title in the book. He's not a professor. He is a doctor, and Frankenstein's monster are things. But this is a classic kind of like, oh, holier than thou blunder, you might hear people say. Well, Frankenstein is the doctor. The monster was never named, and that's true. But you can actually chart the usage of the term the Frankenstein was always more popular, and it stayed more popular. It's still more popular. So we see this increase of this simpler usage as the story gains this broad mainstream appeal over time. We see in 1818 the book was published, so all these begin. 1910 we have a film that sort of marks the beginning of an upward trend. 1974 is along this climb. Young Frankenstein, the parody movie, by the time you are getting parodied by Mel Brooks, you're probably pretty mainstream. And what am I getting at? The point is that you can really do interesting analysis of how people use language by charting how Ngrams go together over time. And another little tidbit of, for this party trick of, yeah, fine, Frankenstein is the doctor, but ultimately you can't argue with the common usage. It just is what it is. This is that tug of war between descriptivist and prescriptivist linguistics. So figure out what side you're on. So back to the kid's speech, right? So we see these are all very common words, word pairings, very common bigrams. And we see that that's pretty useful. And in terms of understanding how common is the language that we're looking at right here, and what kinds of things can we expect if we were to compare it to other language. So n-gram frequency is this inherent property of language. Language is happening, right? And if you chop it up into these n-grams, these sort of paired bits of knowledge, paired bits of meaning, or not even just paired, multiple, 2 or 3 grams, 4 grams, 5 grams, etc. You can look at some of the statistical connections between them, the probabilistic connections. So this is interesting because it can help you kind of tell the difference between common pairings and rare or unique jumps, so more uncommon pairings. You can explore the frequencies of n-grams as they occur in that cool Google Viewer tool. And while we can use an n-grams frequency to help understand its usage in language, this is what I've hoped to describe to you here. But we can also use it to generate language. And this is where we get into actually designing models using n-grams. So, designing n-gram models of language, let's say we want to actually produce some language using the statistical properties of language, right? What features would you need in a system to be able to capture these statistical relationships of language and then reproduce them? Well, something that we're going to do as an exercise here, a very COG-sci flavor, is recall Mars levels of analysis. Describing any one process. It's a fractal thing, so you can slide this up and down, right? The computational level from one thing, one phenomenon, might be the implementational level of another, right? So neurons might be the implementation level of cognition, but they might be the sort of computational level of a cellular biologist's approach, right? But point being, getting ahead of myself, computational level is a very high-level description of inputs and outputs. What is the thing that is happening here? What comes into the process? Roughly, broadly, what is the process doing? And then what's the output? At the algorithmic level, this is more of the specific steps involved to get from the inputs to the outputs. Hint, this is the kind of stuff you have been putting together. Programming is often happily living in the algorithmic layer. And then implementational is how do you actually achieve those steps in terms of the smallest relevant units in the real world. Again, these are scalable. So let's look at the idea of an n-gram model of language from the computational level. If we think of an n-gram model of language as a system with a process, what are its inputs? What are its outputs? And what is a general description of how it's going to work, right? So input to our system, something happens, output from our system. Well, let's start with the model description, a very sparse thing. We already know this because this is what we've discussed, right? So this is going to be a model that's going to learn the frequencies of n-grams in some set of human language, such that it is then able to generate language that is similar to what it learned from, right? So this is taking language, studying it, learning something from it, and then using it to produce new language. Okay, so that's pretty good, and that's a good place to start, but this is sort of our thesis statement, right? This is our broad description. This is our abstract. We have to dig down. So what is the model input? This is the idea of training data. So what it is that you give a language model is very much like what you give yourself when you're studying for a test. Training data, information to absorb, right? This is the have you ever had a dream that, etc. gets fed into our model, this gear right here. And the training data is going to determine which n-gram frequencies your model will be able to learn, right? So feeding that in, we get that U has a certain frequency rate within it, that you had, etc. These are the same from the Google one, but they're relative. Think of them as relative. So that's the input. right? You're going to take training data from the world and you're going to chop and screw it somehow into some kind of internal representation that is useful for the model. Now, what does useful mean for the model? Well, in terms of, we can phrase that in terms of outputs. So the generated language is what we're trying to produce, right? What we're aiming to do with the model is produce language. So this means referring to those statistical properties that we learned from the training data to select new words in sequence. Now, I've included a typewriter as the output, but that's more or less kind of how you think of it. You produce a different word one at a time. Have you ever do not quite the same as the kid, but very close. A similar kind of feedback loop is happening with this kid. So that's the computational level description. We've started to break down this very general idea of how an n-gram model of language might work, and we're digging deeper, right? And now we're going to dig even deeper, right? So we've expanded on some of the basics. Now let's talk about some of the specifics. So what is the algorithmic description of this model? Or in other words, how do we program this up? If you were to sit down at a computer right now, what might you start doing to make this a reality for you? And that's what we're doing. We are from scratch doing this. Now, a note, I will be showing some code here. It's meant to be instructive. It's not meant to be, I cannot promise that it will work if you just dump it right into a text format. It's more to show using the language of algorithmic programming that we've been doing in Python, show you kind of what I mean. So as always, I will walk you through that code. So algorithmic level. This is where we're trying to start to decompose the bigger problem into more elementary steps that we know how to actually solve with code. So where do we begin? In general, we're going to have to find a way to get the language in to our system, right? We have to train on something, right? The training data needs to be taken in some form, right? I'll spoil it right now. It's text. It's strings. That's how we will be doing this in this particular version. We need to figure out what exactly it's trying to learn from the text, right? From the language, the training language. We need to figure out how it's going to store what it learned and like roughly what it is storing. Not roughly, exactly what it's storing. And we also need to know how to use what it learned to produce the desired generated language text. So we're taking that computational level and saying, okay, I know the start point and the end point. Now we're going to have to draw in all of the details of how to get from one to the other. So one note for the algorithmic level is that there is room for creativity. For any given computation, there's almost always essentially infinite algorithms that will work. They're not all going to be as efficient as the others. Some might take more steps. Some might take more space, right? So there can be lots of ways to do things. Today we're going to focus on one particular version of an n-gram model, so just keep that in mind. And to illustrate this, there's lots of different ways to do any given algorithm. In Python, for example, let's say we want to find x to the nth power. We'll define x as 2, we'll define n as 10. If you know your base 2, you know that's 1024, but it's a secret. Now compare these two different versions of how we might solve that. If we were doing this from scratch and we didn't know all of the tricks available to us, we might do something like, well, I need to save x's current value, so y equals x, and then we're going to loop, right? We're going to do a certain number of times, so I'm going to multiply x by itself 10 times, right? That's how we get to a power of 10. So x equals x times y, which is the original value, and so on. That is a legitimate way to achieve a power of 2 in Python. Or not a power of 2, sorry, the power, right? Exponential. There's a simpler way. It's x times equals n. Now, that's a little bit bonkers. You don't need to know everything about this, but that's the shorthand for it, right? If you've seen, we've discussed using plus equals to quickly assign value, right? To append something, to update a number, right? You can do I plus equals 1. You can do x times equals n, and it will take it to the nth power. You wouldn't have known that necessarily, and that's kind of the point here, is that this is a very elegant algorithm, but it takes a certain kind of domain knowledge that you might not understand. You might not have it, right? So which one of these is more elegant, but which one of them is more accessible? One of them is more step-by-step, where everything is illuminated, and it takes more processing time. It takes more space. We've saved a bunch of extra variables. We've got y, we've got I. Whereas if you're doing the exponentiation down here, it's actually like a very low-level process that you just say, hey, computer, go do a bit shift down here at the lowest level. That's all lingo to say there's lots of ways to implement any given algorithm. So we're going to do one today. There are many like it, but this one will be ours. So, training data. What is the training data going to be? The nice thing about this is that it's the easiest one. And that is, you can just work with a gigantic string, baby. Whether it's the Library of Congress or a note in class, text is just text. Text is text is text is text. There are lots of ways to chop it up later as needed. So, the way we will take information in is as text. You could read an entire 10 novels in as a single giant string, or you could read in, just this "Have you ever had a dream?" speech that this kid gave. So that's the idea. This is how we get things in. This is our starting point. This is the language that we want to build a model around to say, hey, I'm going to analyze this and have a look-see. So that's the training data. Now, what do we do with it? What are we learning? What is our model trying to glean from looking at this data? So we've talked about this, of course. This is where the n-grams come in. We're trying to look at how often particular n-grams appear in the training text so that we can ultimately mimic that, right? We being the model, of course, at this point. So to figure this out, the first thing we need to do is to break the text into tokens so that we can look at them as chunks, right, of n tokens, n-grams. So remember that tokens are the words, right, the meaningful units of text, and n-grams are sets of tokens. So then after that, we need a way to capture their repeated occurrences and build up the accrete the distributions of how often each of these tokens, these sets of tokens, these n-grams, occur. We've already talked about tokenization and how we can do that using the split method. So super basic is tokens equals training set dot split, right? Split on the space character. And now the tokens should contain something along the lines of have, comma, you, comma, ever, right? This is a list of strings that all are sort of in the token chunk size. Now, we've got the list of tokens now, at least in concept, so just carrying along our phantom programming environment. Now we need to build the n-grams, right? So sticking with bigrams to start. We could go higher, but for now, let's just keep it a little bit simpler. To do this, you can step through the list of tokens and just grab one pair at a time. And you'll actually be overlapping as you move along. So the goal is to have ultimately a list of n-grams, each of which is also a small list. So rather, you want a big old list of all the n-grams. The n-grams themselves are tiny lists of length 2, right? Bigrams. And then we construct it. We can use this push function. I don't recall how much we've used this in the past, but the idea is that you can add something onto the end of an existing list. Let's do it. So we want to build a list of n-grams. We have an empty list of n-grams. And then we're going to do a loop, right? We're going to step through the list of n-grams. So for I in range 0 to length of token, blah, blah, blah. We need to do this as a for loop that uses an index because we need to be able to look ahead by one, right? We're not just going to look at each token in isolation of all the rest of the stuff. We're going to look at a token and we're going to look at its neighbor, the next token. So we're going to grab both of them. So ng is just a variable we're throwing out here. It's going to equal a list, so open a bracket, token sub I, so the thing we are currently looking at, comma, token sub I plus 1, so the one next to it, right? So at the start of this loop, it will be a 0, so token sub 0 will be the first word, token sub 1 will be the second word. The first n-gram is going to be that pair. And then we will push that onto the n-gram. So the loop was going to do that over and over. Grab the pair, push it onto the set. Grab the pair, push it onto the set. Over and over and over until we have a full list that looks something like this. So open bracket, have you ever, etc. until we get to do anything, right? That's the end of the kid's sentence, right? Do anything, right? He's kind of proud of himself there at the end. So, and then we close the bracket. So this is the idea. This is our set of n-grams. So the first thing we did was we chopped the string up into tokens. The second thing we did is chopped the tokens up, sort of rebundled them up into n-grams. So now we have sets of these meaningful pairs of language. Cool. Now what? Like we continue. So we've chopped up the text into its n-gram parts, right? We're using a lot of space to do this. Like I said, there might be more elegant ways to do this and cleverer ways, but we're going to do this the most explicit way so that it makes sense as we run through this. So our goal, remember, the key thing that an n-gram model needs to learn is how frequently each pair of words, or in this case pairs, but in other cases n-gram, occurs, right? If I'm going to mimic this language, I'm going to need to understand how likely each word is from each other word, right? So remember that sort of step-by-step process of language we're talking about. Words are events, they follow each other, so from a given word, I need to know how likely the next one is. But how do we track that? And where do we put it, right? So, tracking frequencies. The very first thing that might come to mind is we want to do something like Google did, right? We could just come up with this table of numerical frequencies like we see Google doing. This is great. This perfectly captures what we're talking about, the statistical probability of these things in the data. Great. But fast forwarding to our goal, how would we use this table to generate language? I'll tell you right now, it's tricky. So here's the table, similar to the ones that Google can produce for us as well. And here's the generated text. We would start with, say, the first word, have, right? There's only one place in the text where have appears. Okay, so then that means we're going to go to you, absolutely, right? We have to. There's no other place. But now we're already at a conundrum. And that is, there are two places you occurs in this pair as the first word. We're trying to generate a new word, right? Well, now we've got an option between ever and occurs quite often. Ever doesn't occur quite as often. So now we got to take these statistical probabilities, these 5% and 40%. We can make a new rating of ever has a 1 in 9 chance, has an 8 in 9 chance of occurring. This is a lot of mucking around with numerical values after the fact, and it's not helping us get to the destination very easily. There is a route forward, but this seems like sort of a bad direction to go because there's another problem as well. It's inconvenient to learn this statistical table because every time I see a new word, I'm going to have to go and update all the frequencies of all the other ones. Again, there are very elegant ways to do this using numerical frequencies like this, but the basic way that we've already seen it is not a great one. So we will avoid it. What's a different way to do this? Well, even though this is a nice little compact table that tells us the information that we want, we can take a different tack. A different way of representing word pair frequencies is on the right there. Focus on the left for now. We'll want to pick out words that follow previous words, but only as often as they actually happen, right? So an alternative to logging and keeping track of all the statistical frequencies is for every word, you can just store a list of every next word that happens after it. So this is great for a lot of reasons. First of all, it's easy to construct. Every time you see a new word as you are studying this list, you add one to the end of the list. And it's also easy to use to generate text, which we'll get to in a minute. You can just randomly select one. So, for example, have leads to you. And that's the only time have happens and you happens, right? You leads to a lot of different things because the kid said the word you quite often, right? And so there are lots of words that follow you. But on top of that, you notice that the duplicates are still there. So you ever, you had, you could, you do. If we sorted this down, we would start to see, well, shoot, if we are on the word you, there's a lot of places we can go, and it seems to be pretty heavily weighted towards things like the word could. This kid said the word could after the word you very often. We've recorded that here, and that means we're able to now, we have captured that statistical probability, but not using numbers. We did it using a list of occurrences. Now, we are trading space. We are giving up a lot of space. We have to store a lot of text to keep this going. For most anything you're going to do, it's going to be easy enough. Don't worry about it. But but what this is giving us is this ease of processing, and it's very great. So let's pull the car back around to what does the model's memory storage look like? So the model has a memory, just like any one of us has a memory. It stores the things that we've learned and the things that we know. So what does the model's memory look like? The nice thing is that that structure that you saw before might have looked a little bit familiar. We can use a dictionary to make this very easy. The keys to the dictionary represent the first word to each bigram, because we're only ever going to be looking at one word at a time, and we're going to be trying to figure out where to go from there, right? The goal of generating this language is to chain this process together. Again, we'll get there in a minute. So the values are going to be the list of all the second words that were observed from each bigram. So we're going to run through the list of bigrams, and we're going to generate a memory based on it. And let's look at one. So memory starts as an empty dictionary. For each n-gram that we have, that we observe from the text, what I'm going to do is essentially, this is the short version. You might actually try to check these things first, but this is the short idea. Each n-gram has two slots, right? It has the first word that happened and the second word that happened. I'm going to say memory sub the key, right? The first word. I'm going to push the value, the second word that we have, onto its list. The value inside of the given key is in the list. Now let's run forward a little bit so that makes a little more sense. What does this look like when it's done? Well, remember, the keys to the dictionary are going to be the first words of each of the bigrams. So have, what happens after have? You happened one time. Now we're going to get you, okay? So you happens. What happens after you? A lot of things happen after you. The word ever, had, could, do, with, could, etc. Those are all contained in a single list. So now the representation we have here, as we just kind of finish that off, is the way we can talk to this memory now is we can say, hey, I'm on this word. Tell me what the possible next words are. That's fantastic. That's exactly what we need, and that leads us to the final step of generating text. So, our model has now studied some training text and stored what it learned in its memory. Now, what we're trying to do is generate some kind of natural-ish text, right? Some text that looks like natural language. So, let's get back to the idea of words as events, right? So, similar to when we talked about the probabilistic modeling of language, we're going to treat each word as a distinct event. And from each event, from each word, we're trying to leap to one of the next possible words. We're going to do it randomly, but it will be weighted based on what we've seen in the actual language. So, drawing this out, the word have is the first word of this kid's little speech. That one always leads to you, because it has to. But from you, there are lots of options, right? And some of them are much more likely. So it's still possible to go to or ever, right? But it's much more likely that you will land on the word could, because it is more represented in the training data. So that's what we're aiming for. We're trying to mimic the production of one word at a time using bigrams. And to do that, we've captured it in memory. So how do we get it back out? So from the starting word, for example, the word have, we see if it's in our memory as a key. We randomly pick the next word from the list. We make the new next word be the new key, and then we repeat. We just loop over and over. What does that look like? Well, let's import random. Remember, this is Python world, so we're importing the random package. And the idea is that we are trying to use the randomness as the sort of the thing that mimics speech production. So the first key, we'll just start with the first word, as always, and we'll go ahead and print that once out. And then, as long as we're not dead or done or whatever the heck, right, we're going to loop, loop, loop. If the key is in my memory, right, if the key that I have actually was represented in the studied text, then I'm going to grab the options from memory by saying, hey, give me the list of values that was inside memory at that location, at that key. So now I'm going to give the next word is random.choice from the options. So what does that mean? Options is the set of words, right, that are possible from the current situation, from the current word to the next word. Options is a set of words. We're going to randomly choose one of those. And then we're going to print it. And then we're going to say, okay, we're going to start this process again, make the key the next value. So what's happening here? Let's try to trace that. So first of all, the memory is something that we've trained already, right? That exists before this generation step even happens. And while we're trying to produce the words, we have defined two different variables. We have the key and we have the next value, right? So the key to start is the word have. We then use that key to go to memory and ask, hey, do we have anything for this? I'm seeing this word. Have we encountered this word before? And what are the next possible words? Which we pull out in the form of a little list of you. And in this case, we randomly choose the one word that's there. That's fine. So in this case, there's a little bit of redundancy. It's nice and clean. So we have found a word. We have produced the next word. Great. Now we overwrite have. We get rid of have from the key, and we replace it with the word that we chose, you. Now we use you. We are looping now, right? This is the loop. Now we use you to go to memory and say, hey, do we have anything for you? Turns out we have a whole bunch of things for you, which we will need to select something at random. This is the algorithm for producing, one word at a time, a trace that looks like human language. And that's our algorithm. So we have, I hope, now seen how a bunch of lines of code can potentially capture at least one version of an n-gram model of language. So we're taking an input string to train, we're breaking it up into n-grams, we are studying them and extracting their word transitions and their frequencies by storing them in lists, and then we can randomly chain together possible word transitions to make language, kind of like that struggling kid was doing. And this is an output of one of these n-gram models of language. So now let's talk a little bit about the back end, right? So we've gone all the way through how you might build one of these things from an algorithmic perspective. Now let's talk about kind of how the usage works and maybe what the parameters are that we can tweak to this thing. So what might you use this for? We might not use it for much in our day-to-day lives, but there's a few different interesting ways to apply these things. First is just generating text, which is inherently kind of fun and interesting. So we can match or blend different voices, which we'll look at in a minute. And we can also tweak the scale of the n-gram size to different effects, like we've discussed. And we'll demonstrate some of that today. But we also have some applications you've seen in the real world, at least the predictive text, but we also have this interesting idea of sort of flipping this process on its head and using this algorithm, this model that we've created, to do some text classification. Classification is an interesting process of trying to say, hey, I have this model that's trained on this particular kind of information. I can tell you how much your data looks like it. Again, we won't be digging too deeply. We've been at this long enough today, but it's interesting stuff. So, generating text with this thing. The text generated is going to be sensitive to two different things, and they're and a little bit of other stuff. But the two big ones are the frequencies of the transitions between words and the training text. So this is what we're training the model on, right? This is kind of gives it the character of the text, the flavor, the voice. But it's also going to be sensitive to the size of the n-gram. Remember, this is that trade-off between realism and generality. We'll cover that in a moment. Other things do matter. So things like little small-scale implementation decisions, like how do you treat punctuation and white space and new lines, right? How do you handle running out of text and generating a new word from the start, right? Lots of different possibilities there, but the two that are more sort of theoretically grounded are the general frequency transitions, the frequency of transitions, rather, and the n-gram size. So let's look at our little model that is trained on the kid's speech, right? This is bigrams. Have you ever had a dream that we can produce language that is pretty close. It's doing the same things, more or less, that the kid was. It's circling around the word you. It's going to you could, you, that you wanted, ever had to. It does have some question marks in the middle of the sentence, but ultimately, it's doing the same kind of stuff. What, though, might happen if we feed it something else that's not a kid rambling and spinning around in circles, kind of like the model is going to do in general, but we gave it green eggs and ham? Do you like green eggs and ham? I do not like them, Sam. I am. I do not like green eggs and ham. And so on. Everybody's probably heard the story. This guy wants to give Sam a lot of eggs and ham that he doesn't like them. So just lay off. No one needs these green eggs. So what if we do the same thing? The same process of analyzing the bigrams. Do you like green eggs, and producing language based on it? Well, ain't perfect, but you look at it, you drag your eyes over it, you can kind of tell it's Dr. Seuss, right? You can kind of tell what story it is. Now, it's a very short passage. Of course, it's kind of easy to tell based on the words alone, but it's capturing a certain kind of pattern. Dr. Seuss used certain kinds of words. He liked to repeat certain kinds of words. He liked to sort of go with this cadence. We're not going to capture the cadence very well, at least not with a bigram, but we are capturing his word choices, his frequencies, his something, right? Green eggs and ham. I would not like green eggs and ham. I would not like them. I do not like them, Sam I am. He's a little more repetitive in his artificial version, but he's close. He's doing things like the real Dr. Seuss. And this, I hope, illustrates the idea of capturing voices. So each of these models is trained on something different. One's trained on the kid stumbling over his words. The other is on a bit of Dr. Seuss's famous book, Green Eggs and Ham. Both models are using the exact same architecture that we covered today. They're just trained on different input text. They have the same sort of structure. They are both the same beast, but they have lived different lives. They've studied different things. And thus they come away with different voices. We have a stumbly kid versus a wizard with words, right? Now, what if I want to just mush those together? What if I give this model both regular Dr. Seuss and stumbly word kid? Do you not like them? Have you liked them anywhere, here or there? I do. You like them. Would you the dream that that you wanted him to do you so much that you could do anything so you that you could. This is a stumbly Dr. Seuss. Now, it's very clearly still very highly tuned to these two short passages I've given it. But you see how it kind of jumps to and from these different voices. We've introduced a stutter into Dr. Seuss, one thing he was not especially known for. So that's the idea of blending voices. By training on two kind of distinct training sets, but sort of mashing them up together, you can randomly select new text, generate new text based on either of them. Now, it is important that you have some amount of overlap in vocabulary, otherwise they won't be able to talk to each other. If you feed one all numbers and one all letters, they ne'er the twain shall meet, right? So whatever starting word you give it will lock you into one. But this is the idea. This is an interesting little weirdo thing you can do, is if you train a model on a bunch of different piles of text that have things in common, it's going to be able to sort of blend voices together. And that, to me, is just kind of fascinating. I love that kind of thing about this stuff. So, yes, this is the idea. This is the kinds of oddities we can generate using this kind of these kinds of models, these n-gram models of language. Another thing to keep an eye on is n-gram size. So, let's take a look at a chunk of the original Green Eggs and Ham, right? You don't need to read the whole thing. We more or less know how it goes. Let's look at the different n-gram sizes and what they produce. Now, our friend the old bigram, I do not eat them in a goat. You do not eat them in a car. Sam, let me be. I would not like them in a goat. This one seems obsessed with goats. But, okay. We've already seen bigrams of this particular passage, of this particular model. It's doing something, it's doing some work, it's capturing some basic transitions between words, and it's capturing a little bit of the voice used. This one protests directly, says, I just don't want them, let me be. But it's also a little bit gobbledygook, right? It's not really preserving good meaning as it goes. Let's ramp it up a bit. Let's look at 3 gram. I am Sam, Sam I am. I do not much care for this 3 gram. I do not like them with a goat. It's always goats with these models. And and I would eat them here or there. I will eat them in a box. Hey, he's going to eat them. All right. That's actually a problem because we know Sam ain't going to eat these eggs, right? But here he is professing that he will. So this is a 3 gram. It's clearly much stronger at preserving certain parts of the structure. The words I am produce the word Sam, almost always, right? Am Sam produces the word Sam after a character turn. I do produces the word not quite often. It's interesting we see would and eat. We're going to get rid of that if we keep expanding. So the larger units of meaning, things like I would not eat them, they're not as easily preserved by a 3 gram as they might be by a higher order gram, right? So let's keep ramping up. We don't need to stop at all of them for a long time, but here's a 4 gram. I am Sam, Sam I am. That's Sam I am, that's Sam I am. I do not like them anywhere. I do not like them, Sam I am. I do not like them with a mouse. I would not eat them in a tree. Well, some of these lines are, these are complete lines. Look at them. There's no more kind of bungling together paragraphs of sentences. These are more and more structurally the same as the original, right? Let's continue. 5 grams. I am Sam, Sam I am. That's Sam I am, that's Sam I am. I do not like them anywhere. I do not like them, Sam I am. Got caught in a little bit of a backtread of itself. It didn't really move on with the story, but again, increasingly coherently like the original until finally at 6 grams, we've reached terminal gram size. I am Sam, Sam I am. That's Sam I am, that's Sam I am. I do not like that Sam I am. Do you like green eggs and ham? I do not like them, Sam I am. This has become, word for word, the original text. This means that any word you feed it, any 6 gram you feed it, it's just going to reproduce the entire original text. It sounds quite good, and that's only because it's just literally doing the raw, exact same thing that it studied. So it has more or less overfit the original text. Unlike our weirdo friend, the 2 gram, which produced something original, even if it was a little bit garbage, right? So that is the span. And that's the idea of scaling n-gram size. So smaller n means more variety and more generality of the model, but it's less meaningful connections between the words. It can't do this sort of longer unit of meaning type stuff. But larger n means more specific to the exact language used in the training data. It's going to really, really hyper-fit the original data. But it's also a lot more human-like because it's a lot more original data-like, right? And that's all because of what's being captured. The size of this chunk, captured by an n-gram, represents the likelihoods that you're trying to model. Remember that U only has a 0.139% chance of occurring naturally in language, which is, again, a lot compared to its neighbors. But think about that. That's a very slim chance of any pair of words being the words that and you. If you add a third word, that goes up astronomically, or goes down astronomically. More words in a sequence is a less likely event. So it gets harder and harder for you to predict something interesting. Okay, that's enough about the features of the language that you can generate. What is this stuff used for? Well, we're going to quickly touch on 2 different things. One is predictive text. So use this in your phone sometimes. But I hope now you can kind of see what it's doing, right? Every time you type words into your keyboard, your system is keeping track of that as training text, as the input text that we use, right? And then it's going to frequently update its memory so that when it tries to suggest things to you, it's going to give you the most likely words from its memory. Remember, if we had have and you in this model, the word could would be the one that's suggested. It's the only one that makes that's the one that makes the most sense. That's how you can suggest something to somebody as the result of these predictive text algorithms. And then finally, the other interesting thing is the classification tool. So this is kind of neat. You can kind of flip this on its head and use the model's memory in reverse. You can say, for example, for each word in a piece of text, we can determine how likely our model thinks that word is. So that if a model is tuned to a particular voice, say Dream Kid voice versus Dr. Seuss voice, it could compute something like a rating for any given set of text while it tries to predict each word. So we might say, okay, given the word have, what's going to come next? Dr. Seuss might have certain ideas about that. Dream Kid's going to have a very specific idea about that, and that is the word you, right? After you, Dream Kid has very specific things, and every time you get a match, you increase the score until you get to a value of, Dream Kid's voice matched 25% of the words in this set. Dr. Seuss' voice only matched 2%. This is a more Dream Kiddy voice. That's interesting. That's a way you can sort of flip a trained model around and use it for something unique to identify sort of the voiciness of a thing. This is great too because it gets around the idea of trying to produce perfect human regular English language, not just English, but that's the language we've been using, produce natural language. Because it doesn't need to be perfect. It just needs to give a guess for each word. And if it falls off, then it's not doing a great job. But if it gets a score of 90%, it might not look good in human language, but it will look good. At least it'll give it a high score. So that's it. That's the idea. Using n-gram models, we've explained the role of n-grams in language. We took a deep dive into how to construct one of these models inside to outside, and we looked at some outputs and applications and some of the features therein. That is it. Final thought, as always. N-gram models are clearly somewhat limited in the language they can produce, on a sliding scale between hot nonsense and exactly the same as the training text. What differences do you see between the way humans produce language and the way these models work? Are there any similarities? All right, thanks. That's it. Take care.